Good evening, night owls. This is Dr. Nighttime, and tonight we're going to be talking about how to estimate the normal cumulative distribution function with pen and paper. You heard me right. The Gaussian curve, the bell curve, the thing you need a massive table in order to look up, the thing they try to tell you, don't bother trying to get an explicit formula for this. It's not going to work, it's not worth it. We're doing that, sort of, approximately. How good an approximation? Well, this technique, you have to allow for it being off by up to 1 percentage point. Not one percentage point relative error, 1 percentage point absolute error. You know how a cumulative distribution function will always give you a fraction, a decimal somewhere between 0 and 1? So it can be off, this approximation will be off by up to about 0.01. So if you're operating in a range where 0.01 really isn't a big deal, yeah, you can use this. If you're operating in a range where it would be a big deal, probably shouldn't. From what I found, the estimates tend to be pretty good and relatively low relative error as long as you're between z-scores of -2 and 2. But first thing we'll ask is, how good is the central limit theorem? We know that central limit theorem tells us, all right, if I add a huge number of independent, identically distributed random variables, they'll eventually start to look pretty much like a bell curve. We're going to find out, in certain cases, well, one case in particular, how many is a large enough number. Let's look at the special case where our underlying random variable that we keep adding to itself is the uniform distribution, specifically uniform distribution between -1 and 1. Just nice numbers to work with, centered at 0. So we're starting with n equals 1. One of these random variables. Clearly, 1 is not enough. We've got the uniform distribution, it's that red box. We've got the Gaussian distribution, it's this blue curve. They don't look the same. Just looking at the mean and standard deviation, obviously mean is going to be 0, variance is going to be 1/3. Just trust me on that. If you want to look up how to do that, there's plenty of resources on that. But all right, so we compare it to the Gaussian distribution with the same mean and variance, and they're not the same. So clearly, when central limit theorem says we need a whole big bunch, this whole big bunch has to be more than 1. Is 2 enough? Well, as you hopefully know, when we add up two uniform random variables, two independent uniform random variables, we get this triangular distribution. Two of the same uniform random variable. We get the triangular distribution. And just figuring out the equations for these two diagonal lines in order for them to go from -2 to 2 and have area underneath of 1, we figure out that on your way up it's 0.5 plus 0.25x, and on your way down it's 0.5 minus 0.25x. But when we compare it to the Gaussian distribution with the same mean and variance, obviously mean is still 0 by symmetry. Variance has now doubled because when we add independent random variables, the variances add. So it goes from 1/3 to 2/3. Compare that to our triangular distribution, still not the same. So when central limit theorem tells us we need a whole big bunch, this whole big bunch has to be more than 2. Is 3 big enough? Let's find out. So we'll see how, first of all, how would we even get the function when n equals 3, when we've added 3 of these to each other, right? Uniform we know is a box. Triangular distribution we know is a triangle. What about when we have 3 of these? So what we can do, because let's say we wanted to land at some value. Here, suppose I wanted to land at -0.5. Well, my original, when I just had 2 of them, that couldn't deviate from 0.5 by more than 1 in order for me to have any hope of landing at 0.5. What I realize I can do, since I'm as likely to land anywhere as anywhere else within that plus or minus 1 range, right, when I add that third random variable, I just have to integrate from 1 less than my target number to 1 more than my target number. So for me to get the probability density function at x, I just integrate the previous probability density function from x minus 1 to x plus 1 and divide that by 2 because the probability density function of this particular uniform is 1/2 because I'm going from -1 to 1, right? So width is 2, for area to be 1, height has to be 1/2. And I end up with f of x equals x plus 3 squared over 16 when x is between -3 and -1, 3/8 minus x squared over 8 when it's between -1 and 1, x minus 3 squared over 16 when x is between 1 and 3. And we want to ask, okay, does 3 constitute a whole big bunch? Is that good enough? And we look and, well, yeah, it actually is. That doesn't mean for any random variable. Adding up three of them will get this close an approximation to a bell curve. Specifically, this is a symmetrical random variable that we started with, and it was sort of unimodal, right? It wasn't U-shaped or anything. Right? So it's symmetrical, unimodal, continuous. But what that also should mean is if you add up something that has those nice properties, right? If your underlying random variable has those nice properties, but starts out actually looking better, like more Gaussian than a box does, which shouldn't be too hard. And typically, if you start with a symmetrical random variable, it's probably going to look better than the box. That means that adding up 3 of those should also get you a reasonable approximation to the normal distribution. So yes, n equals 3 is good enough. And as we saw before, right, this n equals 3 curve, right, we said that was just these 3 parabolas put together. Well, parabolas are easy enough to anti-differentiate, right? So in theory, that means we should get a reasonable approximation to the normal distribution by, instead of integrating that nasty e to the negative x squared mess, if we integrate these parabolas, that should get us a reasonable approximation. So interesting to note, we can actually subdivide this parabola into nice little shapes. Note that the breakpoints are at -1 and 1. Note also that, and I didn't stress this before, but the mean and standard deviation, right? Mean is still 0. Standard deviation or variance is now 1, which means standard deviation is the square root of that, or also 1. So that also makes it really easy to correspond this to z-scores. And we notice that it's parabolic from -3 to -1. 1/6 of the area is here. 1/6 of the area is on the other side. And then in between, we kind of have this box here. That box has area 1/2, and we've got a 1/6 up here. This means that if you wanted to try to estimate using area of a rectangle and the 2/3, 1/3 rule for parabolas, you also have that option open. But here we'll actually be doing the integration by taking antiderivatives and using calculus. Still can be done pen and paper, though. So relatively painlessly because they're parabolas. So let's do one of these. Let's find normal distribution of -1.5 approximately. Right? So since this -1.5 is in that first range, right? We haven't gotten to the first breakpoint yet. We just have to go from -3 to -1.5. Notice we only have to go down to -3, not down to -infinity, because one of the issues with our approximation is that it actually goes to exactly 0 outside of -3 to 3, right? If we're adding up 3 random variables that go -1 to 1, you cannot get a number less than -3 or more than +3. So clearly you should not try to use this approach for anything more than 3 standard deviations away from the mean. It's a limitation that comes with the approach. But, so we integrate it. We can do a u substitution so that we don't have to juggle this x plus 3 quantity squared. And we get 1.5 cubed over 48 gets us 0.070. Using calculator to compare, right, on a calculator we find, hey, what's the normal distribution or normal CDF of -1.5? It says it's 0.067. So I said you could be off by, this could be off by up to 1 percentage point. This is 0.3 of a percentage point. Okay. Yeah. Let's try another one. If you look back at the graph from before, kind of one of the trouble spots is around here, where this corresponds to x equals 0.5. That's one of the, so that's where you kind of have the most missing area. So if we're gonna mess up big time, it's gonna be here. And so let's see how that goes. Let's try that troublemaker, normal distribution of 0.5. All right, so we integrate. Notice, so we're now in this middle range, right? So in order to prevent needing to do multiple integrations, we also know that by symmetry, right here at 0.5, or sorry, at normal of 0, that's going to be 0.5. So we know that everything out here accounts for 0.5, and we only need to figure out this bit. So we take 0.5 plus the integral from 0 to 0.5 of 0.375 minus x squared over 8 with respect to x. Calculus happens. Do 0.375 times a half minus 0.5 cubed over 24. Crunch that together, we get 0.682. Compare that to the actual value. We could kind of tell it's going to be an underestimate, but it's 0.691. Again, we compare here. This is where our approximate curve underestimates the actual curve by the most. So we can tell that the added up missing area is going to be about as bad as it's ever going to get there. And yeah, it's off by almost 1%, right? 0.9%, which not bad for a worst possible error. However, there is a bit of a hitch to this. Yeah, we can find the normal CDF of a value. Does it, well, shouldn't it work to run this in reverse? In theory, yes, this approximation can be used to run it in reverse and find corresponding percentiles, right? Instead of saying, what's the probability of a normal random variable being below a certain number, we could say, well, what's, say, the 10th percentile or 75th percentile of a normal distribution? Yes, it works for that. I mean, the number that you would get from this would be reasonably okay, but you start losing the ability to really do it pen and paper, and I'll show you why. So if we try to find percentiles, well, what if we want to find the 10th percentile? That's kind of this first case, or it's kind of this first case here where you're in this left tail. So you integrate from -3 to x, right? T plus 3 quantity squared over 16 dt. Do the u substitution. You're setting it equal to 0.1. It gets you the equation x plus 3 squared over 48 equals 0.1. Multiply both sides by 48, and, well, I did not find cube root of 4.8 pen and paper. I used a calculator. So I guess it means that with a scientific calculator you could do it, as opposed to a big honking TI-83 whatever. But as you can see, your ability to use this to find percentiles is limited by your ability to do cube roots pen and paper. But the final answer, -1.31 versus -1.28, they're okay. Okay. Then we run into even more trouble, though, if rather than trying to find something near the tail, if we try to find something in that center range, right, there our integral, 0.375 minus t squared over 8, right, if we're looking for the 75th percentile, we know that at 0 it's 50th percentile, so we only need the remaining 25% to get the 75th percentile. We integrate this, and we get this nasty equation. I mean, yeah, it's just a cubic, but even with a scientific calculator, you essentially need a graphing calculator to solve this one. And almost every graphing calculator I know of just has normal distribution built in. So unfortunately, good for saying, if this is the z-score, what's the CDF? Not good for saying, if this is the CDF, what is the z-score? Not that the answers will be all that inaccurate. They're okay, but the whole point of this was that we didn't need a fancy calculator to do it. The moment we have to say, well, let's just solve the, find the solutions to the function 0.375x minus x cubed over 24 equals 0.25, right? There's no clean way to do that part pen and paper. So and if we want to use a calculator, we might as well just go all the way and say, hey, calculator, what's the 75th percentile of a standard normal distribution? But as far as going forwards and just normal CDF of stuff, again, as long as you're okay being off by up to a percentage point, then yeah, I'd say this is, and from what I found, it only really starts to break down outside the range of -2 to 2 for your z-scores. But as long as you're looking for something in that range, yeah, if you want to try to do this pen and paper, it works. I've used it. Calculator would have been more accurate, but a few times when I didn't have it, yeah. I hope you found this trick useful. And as always, if you like the way I describe things and want to arrange private lessons, click the link in the description. And until next time, this is Dr. Nighttime wishing you a good night.